Welcome to part 2 of the video podcast series on solubility product equilibrium here at Ontario High School. Going to look at how the common ion effect affects solubility product equilibrium. How's that for circular logic? Anyway, stay tuned. The presence in solution of a common ion decreases the solubility of a slightly soluble salt, and we refer to ionic compounds as salts. So let's consider the following system. Calcium fluoride as a solid dissolves to form calcium 2 plus ion and fluoride ion. So CaF2 dissolves to form Ca2 plus 2F minus. If either calcium or fluoride is in solution when calcium fluoride is added, the solubility of calcium fluoride decreases. Well, what we'd like to do is calculate the molar solubility of calcium fluoride at 25 degrees Celsius in a solution, that is for part A, 0.010 moles per liter in calcium nitrate, and for part B, that is 0.10 moles per liter in sodium fluoride. So there's going to be a common ion in each of these solutions. In part A, it'll be calcium. So we start an ice chart first of all. So we write our reaction. Remember, the solid we don't have to account for in the sense that it doesn't have a concentration that changes, so we just put the dashed lines there. Our calcium is going to start out at 0.010 moles per liter, and our fluoride ion is going to start out at 0. Our change for the calcium will be plus x. Our change for the fluoride will be plus 2x because the coefficient 2. And so at equilibrium, the change for the calcium, or the equilibrium concentration, will be 0.010 plus x moles per liter, and for the fluoride ion will be 2x moles per liter. So our 3.9 times 10 to the negative 11th will be equal to 0.010 plus x times 2x squared. This looks like a pretty complicated problem to solve. We have our 3.9 times 10 to the negative 11th times 0.010 plus x times 2x squared. But we want to make a simplifying assumption. X is very small compared to 0.010, and so the 0.010 plus x really is more or less equal to 0.010. So we're going to drop x from the expression to get 3.9 times 10 to the negative 11th is equal to 0.010 times 2x squared. This makes this much easier to solve. So we have 3.9 times 10 to the negative 11th is equal to 0.010 times 4x squared. So x squared would be equal to 3.9 times 10 to the negative 11th divided by the product of 4 times 0.010. When we do that, we get x squared is equal to 9.8 times 10 to the negative 10th, and then we'll be able to solve. Continuing on with our calculation of the molar solubility of calcium fluoride, and our simplifying assumption was that x is so small compared to 0.010 that when we add x to 0.010 in terms of significant figures, we're still going to get 0.010. So we drop x from that to get 3.9 times 10 to the negative 11th is equal to 0.010 times 2x squared. So 3.9 times 10 to the negative 11th is equal to 0.010 times 4x squared. We take our x squared equal to 3.9 times 10 to the negative 11th divided by the product of 4 times 0.010, and we get 9.8 times 10 to the negative 10th. We can then find our value of x by taking the square root of x, which is 9.8 times 10 to the negative 10th. Square root of that is 3.1 times 10 to the negative 5th. We can now go back into our ice chart and fill things out. So we know that the KSP of calcium fluoride which was 3.9 times 10 to the negative 11th. We use that to find our values at equilibrium. For the calcium 2 plus, we would take our 0.010, add it to 3.1 times 10 to the negative 5th. When you do that with significant figures, it remains essentially 0.010. For the fluoride ion concentration, we take 2 times that X value of 3.1 times 10 to the negative 5th moles per liter. So we get a concentration of fluoride ion that is 6.2 times 10 to the negative 5th moles per liter. So when we look at the molar solubility of the calcium and fluoride ions at 25 degrees Celsius in a solution that is already 0.010 moles per liter in calcium ion, we see that the common ion effect decreases overall the amounts of the fluoride ion that's going to be found. So that's what we have there, and we're ready for the next part of the problem. We're now ready to calculate the molar solubility of calcium fluoride at 25 degrees Celsius in a solution that is 0.010 moles per liter in sodium fluoride. We go ahead and set up an ice chart first. The reacting ions are calcium and fluoride, so we're not going to include the sodium ion in this. Our initial concentration of calcium is 0 moles per liter. Of the fluoride ion is 0.010 moles per liter. The change, calcium is going to increase by an amount X moles per liter, and the fluoride ion should increase by 2X moles per liter. So at equilibrium, our calcium ion will be X moles per liter, and our fluoride ion will be 0.010 moles per liter plus 2X. We set up our KSP expression equal to the product of the calcium ion times the fluoride ion squared, and so we have 3.9 times 10 to the negative 11th times X. 3.9 times 10 to the negative 11th is equal to X times the sum of 0.010 plus 2X, and that quantity squared. As we continue to work this problem, this would be very difficult if we didn't use a simplifying assumption. And our simplifying assumption here is that 2X is very small compared to 0.010. So 0.010 plus 2X is essentially 0.010. So we're going to drop X from that part of the expression, and we'll end up with 3.9 times 10 to the negative 11th, which is the KSP value, is equal to X, which represents the amount of calcium, times 0.010 squared, which would be the amount of fluoride ion. So 3.9 times 10 to the negative 11th is equal to X times 0.010 squared. So we solve for X by taking the KSP value, 3.9 times 10 to the negative 11th. We divide that by 0.010 squared, and we get 3.9 times 10 to the negative 7th moles per liter. We can go back in now and fill in our ice chart. Our concentration of calcium ion at equilibrium is 3.9 times 10 to the negative 7th moles per liter. Our concentration of fluoride ion would be 0.010 moles per liter plus 2 times 3.9 times 10 to the negative 7th moles per liter. When we add those, because of our significant rule, figure rule protocols, we know that there's no significant change. So we would leave the fluoride ion concentration as 0.010 moles per liter. Well, we've come to the end of part 2 of the video podcast series having to do with solubility product equilibrium. There will be at least one more part, possibly 2, so stay tuned for those and watch those as well. I want to leave you with a quote from the great scientist Marie Curie. "Nothing in life is to be feared, it is only to be understood. Now is the time to understand more, so that we may fear less." I wish you well.